Welcome to Chapter 6, Nuclear Energy. We're following the textbook written by Walding that follows the Queensland physics syllabus written by the QCAA. So let's get going. Today's little cartoons in our PowerPoint are done by Calvin and Hobbes. They kind of relate to what we're talking about, so you may like to pause and read those cartoons as we go. What are we doing in this chapter? Here's our learning intentions for the whole chapter. We want to look at artificial transmutations and natural radioactive decay and look at the differences between them, how we induce nuclear fission, how we explain a fission chain reaction, such as in a power station or a bomb, talk about fusion and how that's different from fission, and we'll come back to the Einstein's mass-energy equivalence relationship that we've seen before. So, 6.1, artificial transmutation. And Calvin and Hobbes there have got their transmogrifier. You might want to have a look at those cartoons. Okay, let's have a think. Why do we need a fission bomb to start a fusion bomb? And basically what it comes down to is that in order to get fusion occurring, you need a very high temperature in the order of 6,000 Kelvin. And the fission bomb will start that sort of reaction going to create those temperatures in order to allow the fusion to occur to release a huge amount of energy. Alright, let's move on today. So today's task, investigate artificial transmutations including proton, alpha, deuteron and neutron bombardment. So we're going to look at how we're going to bombard atoms with those particles and induce radioactive decay. And by the end we'll be able to define and identify some examples of them. Okay, what's on the screen here is a nice little flowchart of how we're going through this lesson. We're talking about the idea of transmutation, and that's when an atom is changed into another through nuclear decay. When we spoke about in Chapter 5 around natural radioactive decay and how that occurs and how we have alpha particles and so on given off and beta particles and all that, when the atom actually splits in half or splits apart, it doesn't have the same number of protons per atom in each nucleus, so therefore it's a different element. That's what we mean by transmutation. One atom becomes another one because it splits apart and has less protons. So when we look at nuclear radiation, the top row here is sort of what we've discussed before. Natural radiation is the normal radioactive decay, an unstable atom. It either has too many protons or it has too many neutrons, some sort of arrangement like that, and it'll split apart. Today we're going to look at the artificial transmutation, where you actually bombard or shoot particles at an atom. We're going to look at how we can shoot protons at atoms, an alpha particle, a deuteron. A deuteron, you'll call from deuterium, is basically like a hydrogen nucleus with an extra neutron. So it's like one proton and one neutron. That is the atom that we're shooting at a particle, at a substance. Or you can bombard a particle with neutrons. So we're going to go through all of those, and this little flowchart will appear up in the top corner here of our PowerPoint, and you can follow through as we go. So, proton bombardment. Fairly straightforward on the left here. We start with the proton, we shoot it at another atom. We will give off other particles. So this lithium atom here is going to split into two different particles here. In this case, it's splitting into alpha particles, but we're also releasing energy as that occurs. And it should be noted that this proton that we started with ends up in our equation because it appears there. So the proton is bombarding the lithium-7 atom, and it splits into two helium atoms, and obviously there's energy released, which was shown with the gamma radiation given off there. That's proton bombardment. He's done there. Alpha bombardment, where we shoot an alpha particle at a substance, at a sample. So the alpha particle here is shot in this case at beryllium, and what happens is, if we look, we have two protons there, 4 there, 2 and 4 make 6, so that bit's balanced. You can check the top bit. 4 plus 9 is 13. We have 12 neutrons there, and we have a neutron given off as a free particle. shown down the bottom here with our equation, our balanced chemical equation. Helium alpha particle plus the beryllium gives carbon plus the neutron. Got another example over here where we're using nitrogen, but in that case a proton's actually given off. Now, if you think ahead, there's a proton given off there, but we've already spoken about how a proton can induce radioactive decay. So if you think what happens to this particular proton in your sample of nitrogen that's slowly decaying into oxygen, it's going to bombard another atom eventually. And we've got neutron in here, we've got a neutron here, that's going to interfere with other atoms as it goes along. Deuteron bombardment. So recall, deuteron is like a hydrogen atom with a neutron added. So in this top scenario here, whoops, there we go. We've shot a deuterium atom at mercury, and what we've done is we've made gold, and that is the transmutation that we've done. Once again, 1 proton plus 80 protons, 79 there and 2 there, so it balances. And if you look at the top numbers, the 199 plus the 2, it's obviously 201, which is him plus him. Now, that made gold. That's gold is atomic number of 79. He's on the upper side. On the lower side, we've got this guy here, platinum. So when we bombard our deuteron at our platinum, we end up with a gold particle as well. Gold's obviously valuable, but the problem with this reaction is it takes a lot of energy to bombard it with the deuteron particle. Hence, you're using more energy than what you're gaining at the other end. The resources required to make the gold cost you more than what the gold's worth at the other end. Alright, so that's that one done. And neutron bombardment. Basically, we're shooting a neutron at another atom. Here we are with beryllium and neutron, and what we end up with is lithium and an alpha particle. That's lithium-7. And the question down the bottom here, are these products stable? Lithium-7 is stable. I think about 92.5% of most of the lithium on this planet is lithium-7, so he's relatively stable. But obviously this alpha particle represents a bit of radiation that we're losing. The middle example here, neutron collides with uranium-238, and you end up with uranium-239. Even more unstable, so that one will go through radioactive decay. And the last one, cobalt-59, we shoot a neutron atom at him, and we get cobalt-60. Cobalt-60 has a half-life of about 5.2 years, so he is unstable and will start to go through the radioactive decay, as we will show in this equation here. So the cobalt-60 there is this one here. Too much mass is going to start to decay, and we have an electron, an antineutrino, and gamma radiation. Okay, there's a few websites there with a bit of further reading. I hope you're following with our Calvin and Hobbes as we go through this. These websites here will give you a little bit more background about what I've been talking about. Now, quick question to review. We've spoken about alpha, proton, neutron, and deuteron bombardment. Why haven't we spoken about electron bombardment? Have a think about that. The answer is an electron is so much smaller. Remember, the electron has about that much mass of a proton. It is way smaller, very, very tiny, so hence it just doesn't have enough mass to cause these reactions to occur when it hits another nucleus. So, did we do our aims? Yes, we did talk about artificial transmutation, where we bombard an atom with a proton, an alpha particle, a deuteron, which is a hydrogen atom with another neutron, or we shoot a neutron at it. And we've given you plenty of examples of what this looks like. So your task now is get on with check your learning questions. Don't forget the note I've got down the bottom here. Have a plan about how you might handle the next section. Read over the first part of the chapter at least so you know what's coming. Okay, thanks for coming.